I'm really happy to be able to introduce Scott Lindvall, who is here on behalf of AEG. He is their distinguished lecturer this year, and that's part of the Richard Johns program through AEG, so thank you so much for making the trip. Scott comes to us, he's a Californian.
Yep.
Went to college at Stanford and then did his master's at San Diego State. Has worked in Northern California, Southern California, Turkey, lots of experience looking at earthquakes and structural geology, and is going to talk to us about the San Andreas Fault and the security of the LA Aqueduct. So, thank you again.
Thanks, Rachel. This will be a presentation that will cover the San Andreas Fault crossing for the LA Aqueduct that brings water down from the Owens Valley to the city of Los Angeles. So I'm just going to go through, this is kind of some of the things that I cover. I do start every talk off with a couple slides on Dick Johns and remind everybody who Dick Johns was. He was a phenomenal individual, and that's who this lectureship is named for. A few slides on the LA Aqueduct history and overview, and then we get into the Elizabeth Tunnel crossing. It's a 5-mile long tunnel, crosses the San Andreas at about a 300-foot depth. But we did a multi-year investigation starting with surface mapping, then we moved into phase 2 with subsurface exploration. Then on top of that, it's looking at what kind of displacement should they be expecting or design for their future fix to make this system more resilient. And I'll get into the displacement hazard analyses and the results. So Dick Johns was a man of many talents. He published in every one of these research areas and was an expert in several. Engineering geology was a big one. Mineralogy was a big one. His model on pegmatites, I think, still holds true today, and how they form. But not only was he a great research scientist, he was a phenomenal teacher, and then his latter part of his career, he did a lot of consulting with a lot of different consultants, but really trying to translating or applying his knowledge to the built environment. As I mentioned, teaching. The most dynamic professor I'd ever had. I was fortunate to have taken his engineering geology class. He put geologists and engineers together in that class, and in teams. And so his philosophy was, look, this is how you're going to have to work in the real world. You guys know how to learn to talk to each other and work with each other and understand the needs of each other. But I don't expect geologists to become engineers or vice versa. So,
who won that fight?
Pardon?
I said, who won that fight?
Well, it was, and he laced these problems with a lot of humor, which made everybody very eager to jump into these things. So, Dick was, he was also Californian, grew up born in LA, graduated up in Seattle High School. He came back down to do his BS in geology at Caltech. But the interesting thing is, he was a chemistry major up through his junior year. And in 1 year's time, he was able to complete his coursework for his undergraduate degree in geology. He had to stay on after that 4th year to do the summer field. But I think that just shows what an incredibly capable guy Dick was. He worked at the USGS. He came back to Caltech to get his degree and PhD in geology, but he got a minor in vertebrate paleontology. He became a professor at Caltech, then moved back to Penn State as the chair of the department, came back to Stanford University as the dean. While he was there, he set up the Applied School of Earth Sciences. So again, another good reason why this applied lectureship was named after him. Unfortunately, he passed away in my senior year, but at a young age of 68. I just want to highlight, I didn't do all the work on this project, on these big consulting projects. They really utilize a lot of different people. And so I'm going to present both the results of phase 1 and phase 2 that was with the Los Angeles Department of Water and Power. And they're geologists. They have a geologic staff, unlike many utilities. URS was the prime, and we at LCI were a sub to the prime. Phase 2, the contractor was a little different. AMEC Foster Wheeler took over as the lead, and then we were a sub along with AECOM. And that was just recently completed in January 2019. Keep forgetting I can advance with this. A lot of key people. Like I said, the department has a staff of engineers and geologists in the geotech group. AMEC Foster Wheeler, Scott Kerwin was the PM on this and managed to collect a lot of field data on this. USGS, in a cooperative agreement with the Department of Water and Power, and also helped on this as well, and other folks. I just want to give people their due. We presented some of this at EERI a couple of years ago, but before we were finished. So the overview of the aqueduct. The aqueduct is shown here. Los Angeles is cut off here in yellow, the city of LA, and this is the department it's a city department, the Los Angeles Department of Water and Power. And it draws water from the Owens Valley, which is on the east side of the Sierra Nevadas. You can see some of the pieces of the aqueduct. Elizabeth Tunnel, where it crosses the San Andreas, was completed in 1912. And this diagram also shows you some of the historic ruptures in red that had ruptured either before or after the aqueduct was constructed in the region of the aqueduct. It was completed in just 5 years, which I think is an amazing feat. If we tried to do this today, it'd never happen in 5 years. And it'd be billions of dollars, not millions. This is a photo of, I believe, Elizabeth Tunnel. These are some of the siphons. It's a gravity-fed system all the way from Owens Valley down to Los Angeles, so they had to go up and over topography. They do have some siphons. This is the Cascades coming into the northern end of San Fernando Valley. The aqueduct, like I said, the whole thing was completed in 1913, at least the first piece of it. They've added things since. But it included a lot. The aqueduct itself was 233 miles, lots of unlined open channels, lined open channels, concrete conduit, lined tunnels, which the 5-mile-long Elizabeth Tunnel is part of, and 8 different reservoirs, both for storage, and then the ones up in the Owens Valley are really to moderate flow on the aqueduct. And in fact, Haywee dams, both the North and South Haywee, they were constructed to get up over a high at the southern end of Owens Valley. That high served as the Pleistocene sill for the old lakes that spilled into Searles Valley, Panamint Valley, Death Valley, overflow from Owens. So that was why they built those 2 dams there, to raise the level of the aqueduct in the storage pool so it could flow over that. They built a second aqueduct in 1970, and really it's from Haywee south, the southern end of Owens Valley south, just to add dual capacity piping and capacity for flow. But that also then ducts back in and flows through Elizabeth Tunnel. And here you can see Elizabeth Tunnel. Here's first aqueduct, second aqueduct. It delivers water to the northern end of the San Fernando Valley, and this is the funny-shaped city of Los Angeles boundary. But in addition to the LA aqueduct, 2 other aqueducts really they supply the LA region with 85% of their water, or our water. And that's the state aqueduct DWR operates. The State Water Project comes down here, crosses the west branch, the east branch, and then we have the Colorado River Aqueduct operated by the Metropolitan Water District, bringing water in from the east. As I mentioned before, significant earthquakes, 2 of which occurred prior to the construction of the aqueduct system. Both the 1857 San Andreas event and the 1872 Owens Valley earthquake. We were talking earlier about the ridge crest filling in this gap here. And we've had some out in the desert, but more notable are 1971 and 1994, the San Fernando and Northridge earthquakes. Here is the actual crossing of the tunnel, 5-mile long tunnel. They ended up constructing it by coming in on both ends, and they met not in the middle, but the amazing thing is they met. I'm still amazed at construction methods you could do that in those days without all the fancy electronics that we have today. But this is in what's called a rift valley. It's not a rift valley, but it's just a narrow valley that's parallel to the fault, coincident with the fault. This mapping shows what the fault zone looked like after we got finished mapping it subsurface. Keep forgetting I could advance with this. So the tunnel itself is on the order of about 3 meters in width across, 2.9. It's a little taller than that. However, you can see what the problem is. San Andreas produces large earthquakes, several meter displacements, and you can easily sever this tunnel that's at 300-foot depth, and then the water, the spigot shut off for the city of LA. The rocks to the north are mainly Cretaceous quartz diorite, and south you also have Cretaceous quartz diorite, but you also have Mesozoic gneiss and Cretaceous granite. Unfortunately, the rocks, some of those rocks look very similar. It'd be nice if the North American plate and Pacific plate looked wildly different and make our job easier in interpreting the borings at depth. But unfortunately, when they did the construction, they did not focus on spending a lot of time mapping the tunnel. So there wasn't a good geologic map produced. It would have been nice to have that. But again, I think what we discovered is there weren't obvious. The fault zone were cataclasites, so it was still fairly competent rock. It wasn't gouge and clay and things that where they would have noted those things in the construction records. So the issues on this project that we had to address were characterizing the fault at depth, at the tunnel depth. I mean, we can map it at the surface, but faults usually coalesce and narrow with depth, and we really want to know where is it at the tunnel, not where is it at the ground surface and how wide is it up top. We needed, for their future design considerations, to characterize it there. We also had to characterize the displacement hazard. What kind of displacements are they looking at? We did both probabilistic and deterministic displacement estimates. And we did a first round on the phase 1 to give them a ballpark. Then the department was developing the design criteria that came out in 2018, 2019 was finalized, but we then, in this results here I'll show you today, we followed their design criteria, which is performance-based, more significant or critical structures had to be designed to higher standards. This was the highest criticality factor of 4, but as I'll touch base on later, that we got some very large displacements and kind of had to use some judgment on how to interpret them. And then the reason we're doing this is so that they can plan for how they're going to design something to mitigate this and make this whole thing more resilient. So there's 2 parallel strategies they have. One is a short-term fix, which is less expensive, and the whole design is predicated on the fact they've since changed it. So it was going to be a 30-inch HDPE pipe, plastic pipe, anchored to the inside of the wall. Well, they're going to put 2 smaller diameter pipes, top and bottom, but they're anchoring it to the wall for about, I can't remember the length, about 800 feet. So you span the fault. The whole idea is you've got a straw inside the tunnel. If there's this earthquake that happens before they can get around to the long-term fix, they'll have maybe a chance at passing water through the tunnel. As can be seen here, you can actually get more than 3 meters if you have multiple strands, and this flexible pipe would then hopefully withstand that displacement. If we get 5 meters here and it's a pretty narrow zone, it's going to sever that pipe too. The interesting thing, it's the same time, Kate Scher and others up at, working at Fraser Mountain, about 30 kilometers north, we're coming out with some new results on the paleoseismic data, and I'll show you that. But it really says that the 1857 rupture, which was probably a 7, 8-ish type earthquake, is not the norm. It's not the characteristic event that we've often thought it is. Some of the earthquakes that have ruptured this section of San Andreas have actually been smaller, about 7.5, even 7.3, given the correlations between trench sites up and down the fault. The long-term strategy, however, is something they're still working on. And that's what this study that we're presenting today was really designed to characterize for them. So they want to ultimately design something that's going to withstand the next earthquake. And we know the southern San Andreas is 10 months pregnant, so the hope is they get this done, but this is going to take many years, several years. They've got a plan for it, they've got a budget for it, and construct it. It's going to take several years. So that's what's motivated them to say, is there something we can do to improve the capacity or the resilience of the tunnel? So I mentioned the behavior of the fault, and this is a correlation diagram of earthquakes along this portion of the fault. So on the x-axis is distance along the 1857 rupture from Parkfield in the north to the southeast. The vertical axis is calendar years, starting present and going back in time. 1857 is this uppermost earthquake. And actually these are the individual paleoseismic sites up and down the fault. Bedard Fan up in the Cruiser Plain, Fraser Mountain, Elizabeth Tunnel location is shown here, Pallet Creek, Wrightwood. So there's a couple of really interesting things that came out of this work. One is that, and it's just purely coincidence the way Kate Scher et al. Drew this diagram, was they just took the ruptures that were recognized at Fraser Mountain, but not recognized at Little Rock or Pallet Creek. They just stopped about midway. It just so happens that our tunnel is about that spot, so it's coincidence. But it does tell us that if the department gets this other shorter term mitigation built soon, they might be able to withstand an earthquake if that earthquake is dying out and tailing off near the tunnel, which several of these have. So when you look at 1857, which appears to be the biggest earthquake, there's another one back here at 15, a little after 1500 that is similar in extent, but a lot of the others appear to be shorter, and so that's why it's the 1857 doesn't seem to be the characteristic type event that's just repeating in that length of rupture. And the more common size is about 7.3 to 7.5-ish. And so it's possible that you might get, especially at the tail end of these, displacements less than the diameter of the tunnel.
I'm sorry, what were the black lines? What did they represent?
Oh, sorry, thank you. Black lines are the age dates, the range of the dates. So how these are constructed is if you have radiocarbon dates above and below the event horizon, you have a span of time that that earthquake occurred at that site. And as you compare them up and down the fault, other sites may have better age constraints, and you can actually then start trimming things to get a narrower band by combining things up and down the fault. Those are the age ranges. So in the past 1,000 years, there's been about 5 to 11 ruptures through the tunnel. Again, considering 11 if you consider every one of these passes through, or 5 if they all stop short here in this area. And 2 earthquakes for sure. It's permissible that maybe 4 could be almost as large as 1857. Here's the slip that was occurred in 1857. This is Kerry C's seminal paper in 1978, where he went through and walked the whole fault, looked at air photos along the whole fault, and measured geomorphic offsets that he thought he could attribute to the 1857 earthquake. Our tunnel is located here, and unfortunately, remember I mentioned we're in that Rift Valley, parallel drainage, so we don't have any streams crossing the fault. So for several kilometers in either direction, we don't really have any good quality, any measurements, actually. But given this slip distribution, we're probably in the order of 3 to 5 meters, probably, in our tunnel site in 1857. This Steve Wisnowski compiled the entire distribution here shown in this curve. More recently, however, Zelke et al. Have taken Lidar and done a more quantitative job at looking at the displacements, and they found a lot more. They also reinterpreted this 9 meters up here in the Carrizo Plain, and there's also another study that did 3D trenching by Sina Noctus that showed that it doesn't really look like that had 9 meters up there in the Carrizo Plain. It was more like 6. So now the interesting thing is, you younger folks, your students now, this technology is wonderful. You can do all sorts of things with it. However, anytime we're looking at geomorphic offsets, you got to think about how did those form. Okay, so there's a little gully, a stream that cut a gully. The earthquake ruptured, and so you offset it. Now, every rainstorm or every wet winter, there might be some water, so you're going to modify that. So again, geomorphic offsets, sometimes they're beautiful, they're pristine, they're absolutely believable, but others, so there's been some others who've gone out and looked at these interpretations and said, well, this is good, but boy, we're geologists, we're standing on the ground looking at this, we don't have nearly the degree of confidence anymore. So again, the science is continuing, but the bottom line is large displacements. So the second phase of the study, the first phase looked at air photos, Lidar, we mapped the whole tunnel length. They were worried about, interested to know were there any other faults that might break the tunnel. Second phase came back and focused on the main San Andreas at the crossing. And so we looked at historic air photos before and again, and Lidar, and we also reinterpreted this after we had this subsurface information. We did CPT transects across the fault to sound out both the depth of the rock as well as stratigraphy within the alluvium. CPTs, I should back up, cone penetrometer tests. Instead of an auger or a core hole to get samples, it's a rig that pushes a probe. It measures tip resistance and sleeve friction, and based on those properties in the soil, it can describe what the soil type, behavioral type is. So that's commonly used in geotechnical investigations, but we use it a lot in fault studies because you can economically punch in several of those for every one boring that's logged. It's a lot quicker. We got the big piece of this was 7 angled core borings ranging from 400 to 550 feet. That was designed to go across and through the fault zone. That was continuous core, and we got beautiful core recovery, over 95%, which we didn't think we'd get through the fault zone, but it was quite good. We did petrographic analyses to help classify the fault rock textures, which became really apparent. We had to redo, after the geologist logged all the holes, we realized after looking at the core, when we're all sitting around looking at it, we didn't have nice clay gouge that said, oh, here's, screened, here's the fault on the plate boundary. We thought we were going to see that. So we had USGS geologists, our companies, the other consultants, we had the Department of Water and Power geologists, we were all looking, okay, where is the plate margin? And it wasn't obvious to us. And I'll show you some pictures of the core. But down each one of these holes, we ran resistivity, E-log, suspension logging, and acoustic televiewer. In hopes of acoustic televiewer, in hopes of seeing, actually getting bedding, orientations of these, not bedding, this is crystal rock, getting orientations of these faults. But none of these really were very effective. And this is, again, we just learned on the type of rock and the type of the way the fault zones were expressed. However, resistivity worked beautifully. every low spike in resistivity we matched to a cataclysite zone in the fault. So that proved to be very useful. This is the crossing area, just showing what previous mapping had depicted. Just simple strands, they're dotted, concealed under young alluvium, not very well expressed in here because it's been graded. Even back in the oldest air photos, go back to 1928, man was out there mucking things up, digging ponds, planting orchards, moving some things around. So unfortunately, it wasn't the most pristine ground surface to work with. This was the fault as we mapped it in phase one. In phase one, we just were looking at air photos, Lidar, lots of question marks as we get east of the tunnel. We had a good scarp that we felt confident in right here. This, and we're showing the CPTs and borehole locations on that first map of their phase one just for reference. But here's what we ended up with as a fault zone defined by the borings. And this is not at the ground surface, this is actually at the top of rock. So we're trying to define the fault zone at multiple levels. And it looked quite different. This just shows a couple of pairs of air photos from 1928 on top and 1948 below. You can see, unfortunately, there's a lot of tonal lineaments in here that are man-made. This happens to be a fence line right here. This is a pond that they had begun digging. So unfortunately, man was busy out there mucking with things, but there was this persistent fault scarp that we could pick out on the air photos to the west of the tunnel. The final map interpretation is shown here with the tunnel in blue and the faults in subsurface in blue. But here's what the Lidar looks like without any interpretation. And you can see all the grading that has been done more recently. Very, very little expression whatsoever in the zone. However, if you go off to the west, beautiful scarps, 3 scarps marking the northern margin of Hughes Lake. You go off to the east in Munn's Fans. There's a scarp here and this young Holocene fan, and then one over here. Again, you can walk out there and see these as well on the ground. But this is the final interpreted zone that we had. It was at the end of the project. Okay, this map now focuses in on the tunnel right here in the subsurface, and these are structure contours on the top of rock. So top of the granitic and metamorphic basement rock, below the alluvium, and we've definitely got some structure here, a very linear drop off or ridge here. We've got this block here. We've got successive downstepping of the bedrock surface here. So we ended up mapping faults in the subsurface with the top of rock. And I'll show you the next couple of figures. I will show you 1, 2, and 3. These are these profiles. This one in heavier yellow is the angled core hole profile, which we'll get to next. This is how this one is very clear. We've got all these CPTs are bottoming into rock and hitting refusal, and there's a very abrupt step in the top of that rock surface. So we interpreted a fault here, and there may be another one right here. This is off to the west. As we move closer to the tunnel, this is transect 1 and transect 2. Again, you've got this lower, and then you get the big abrupt step. There are faults in here and here. And then this is closer to the tunnel, transect 2. We've got faults on the north end of this block, and then in here and in here. And we also added cores in here, and then the angle borings 100 feet away, so we've got some of these faults pegged. The CPTs, however, when you guys are out in industry and working on things, CPTs can get hung up on gravels. So you're trying to push through and you get a gravelly lens, they're going to hit refusal, and you might say, oh, it's rock, it's bedrock. Well, no, it's not. So we also, on this particular one, had 5 hollow stem auger cores to go grab rock, and we can confirm that. All of these were within, that we did check, were within about 1 to 2 feet of the actual rock surface, so they're very accurate. Further north off in the pond area, though, we did get refusals high that we threw out and did not use in structure contouring the ground, the bedrock surface. So the faults, as I mentioned before, were defined at multiple horizons to develop a 3D model of this zone going down to the tunnel. One at the ground surface, looking at historic air photos and Lidar. That was unfortunately limited right at the tunnel location. The alluvial stratigraphy, lateral changes in the CPTs, and we did a lot of age dating throughout the section. Most of it was Holocene, but we did have some lower parts in places. The deeper parts were latest Pleistocene in age. So therefore we said, okay, anywhere we're going to get a bedrock step, we're going to consider that an active fault, something that's, the alluvium is not that old. The buried bedrock surface, we had abrupt steps defined by both the CPTs, Hollis demographic cores, and the angled core borings. And then the other one with the fault textures. As I mentioned, we ended up having to go back and really mapping these fault textures. We lay out all these cores individually as we complete the hole, and then we lay them all out again side by side in a field, so we can really look at, okay, does this look like the same zone of rock that we have in this next hole, and try to help add confidence to our mapping and correlating between borings. This is an illustration of the resistivity log on the left, and it was these lows that really picked out these zones that were faults, and they were cataclasites. This is a cataclasite, a foliated cataclasite, 5-foot stick of core, competent material, but milled and ground to mainly clay-sized particles, remineralization. And so that's why this material was not giving us signatures in the E-logs or the suspension logs or the acoustic televiewer. It really didn't have properties much different than the damaged rock, where you could start making out, when you get outboard of these zones, you could start making out some crystals. And so we did over 50 thin sections to really get a handle on the rock texture. This is a core that's got foliated cataclasite here in red and ultra cataclasite where you've almost pulverized you've milled everything down. And so this is earthquake after earthquake, breaking rock, busting and rolling grains to where you're milling it down to nothing. So it's a physical process of milling this rock, pulverizing it. But it also has some heat and frictional and fluid aspects to that as well. Not something we addressed, but other researchers are looking at some of this core to try to answer some of those questions. So the fact that we didn't have clay gouge is a real curveball, as I may have mentioned earlier. It was kind of had to make us retool, and that's why we did these 50 thin sections. So we go back to all the core and have confidence that what we're calling a fault is cataclasite or ultracataclasite, and distinguishing that from the other damaged rock. This is an illustration of the fault zone. As you can see, it's broader at the ground surface, or this is the ground surface. This is the bottom alluvium, which is somewhat of a cartoon. But you can see it's a broader zone at the surface, and it's coalescing and narrowing with depth. That's typical of fault zones. Here's section. Here's some fault damage rock. Here's the actual core sample. You can see, nice grains and things. This is an ultracataclasite, and it's just pulverized. You don't recognize any mineral grains. You've got some, remineralization that's occurring through this mass, but it's just very, very different. And so we did this as a benchmark so we could macroscopically categorize things in the cores as we marched along. This is the chart of the textural classification of fault rocks from Simpson. And so the only thing I want to point out here is that we identified ultracataclasites, cataclasites, protocataclasites, and we did not get entailed in trying to look at what the grain size was on the breccia. we couldn't map that macroscopically, so we just lumped all this into fault damage rock. But this is increasing deformation vertically. The only thing I should add here is that later on, Chester had improved this rock classification scheme to include foliated cataclasites, because that's what we saw, and they're quite impressive. So going back to the map view, here is the tunnel, and this is the zone of angle, or the transect of angled cores that we angled north across the fault zone. Well, we ended up, and I'll just highlight this now, we defined a zone, and the faults in this map are shown at the top of rock, on those structured contour surface of the top of rock. But these zones of the principal fault zone and the secondary zone of faulting, where they really got to start mitigating the fault displacement, that is really mapped at a lower level at the tunnel. So we're mixing things on this map. I just want to point that out. That's why these aren't centered on the faults. And here's that cross section. This is simplified to where we just mapped, color-coded, based on cataclysite, ultracataclysite, cataclysite, protocataclysite, and fault damage rock. Yellow being fault damage rock, and the reds and the purples being the ultracataclysites. So this, and here's the tunnel depth here, again 100 feet away. We wanted to stay 100 feet away. We didn't want to poke holes in the tunnel. Things can wander. So we also could use the stratigraphy from the CPT work, and they readily identified a lot of, there were some man-made ponds out here now, but there was also ponded alluvium, fine-grained deposits that were occurring naturally in this valley up against the fault. And so that's what's shown in blue, is a distribution of ponded alluvial deposits that had greater than 50% fines, clay and silt. And you could see how they're just ponding up against the main fault zone here, with some small pieces back in here ponding as well. This is the same. I just want to point out that in AC1 we counted a 6-foot length of cataclysite and ultracataclysite that represents the main fault zone. And that's just above the tunnel depth. And what we ended up doing is correlating these big, obvious cataclysites to one another. And there were vertical steps in the bedrock here. There are big faults in the cores here, 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 and here, as well as down here. Down here was a little more, not quite as obvious. There were a couple more zones. But we also had a very pronounced feature here, which is F2. So again, when you go out there and you're working on projects in the real world, you're never going to have enough data. You always want to have more. You want to have more uncertainty, or more certainty, and reduce the uncertainties. But again, this exploration program was about $1 million. It was a lot of money. And so while it'd be nice to say, yeah, we'd like to add about 3 or 4 or 5 more, really wasn't going to happen at this stage of the game. So, but these were invaluable at figuring out what the fault zone looked like at depth. Are we correct in exactly how we've connected things coming up to the surface? We may not be. But the important thing is, where are the big faults near the tunnel? And we've got that constrained pretty well. Out here to the north, there may be some more faulting. But again, because the acoustic televiewer couldn't tell us dips and orientations on those things, we're just connecting things with question marks, because it ought to be a high angle fault. It's the San Andreas, but there easily could be lots of other little things out there. That, like I said, the rock's laced with these little things all over the place. So the San Andreas has been operating for several million years. Some of these may no longer move at all, ever. The other thing I would add, that the assumption is that these big zones are where they're happening still today. There have been a few studies post-earthquakes, one in Taiwan and a couple others, where they drilled the fault after an earthquake. And they're finding that in some cases, it's just a couple millimeters is the slip surface that carried like 3 meters of slip. And they can tell that because a couple of reasons. One was there's still a thermal signature on that plane in the core, a little bit warmer than the rest. So again, that frictional heating hadn't quite dissipated. But so especially if say we're kind of a little complicated zone. There's more faults than we thought, and if we could excavate down, remove all the alluvium, vacuum the rock, I'll bet we'd have a little different interpretation here. The question is, would it matter for the tunnel? And hopefully it wouldn't. But so that's the characterization of the fault zone itself in the subsurface. There's basically that big F1. There's an F2 that's about 35 feet south. We defined that 150 foot wide a zone of principal faulting and incorporated those two faults. Now again, we're 100 feet away. Things can change along strike, so we're trying to say that at the tunnel, you got 150 feet length of that tunnel where that's where the fault's going to be, the big principal fault. And we defined a secondary zone almost 500 feet in width, where they should expect to have some secondary displacement. So now let's look at the design guidelines that they recently adopted as performance-based. This is a critical structure, class 4, the most critical, and what they want is, this is for all their facilities, existing, new, they want the criticality for design with a 2% 50-year probability of exceedance, which is a 2475-year return period equivalent. That's in probabilistic sense, space. And they also wanted an 8.3 scenario. Now, we've never seen an 8.3, but that's what the USURF-3, the Uniform California Earthquake Forecast, has those size events in it, so that's what they selected. We built a fault model that has, from the park field all the way down to the south, that includes multiple rupture sources, and this is a way to accommodate, this is the seismic source characterization that you need to do before you do the fault displacement analysis. The sum of all those allows for variable slip rates along strike. Only 5 of those rupture sources actually cross that tunnel. So those are what are formally characterized, these different rupture sources, and a slip rate is apportioned to each one of those. So that's the engine that drives the probabilistic values, is what's the slip rate. I won't bore you with the rest of it. The results. Here's a hazard curve, the mean hazard curve resulting from the probabilistic analyses. I'll show you tables of these values, but these are the fractals. So you could say, at say 1,000-year occurrence interval, your mean is about 10 meters. And here's your uncertainty of all those different branches in the logic tree. Fractals ranges from the fifth percentile of about 7 meters all the way out to 95th percentile, probably 17 meters. This is a log plot. Again, very big displacements. Let's look at it deterministically. So then this was not just a straight deterministic analysis where you take a regression analysis, plug in a magnitude, and get out a number of average displacement. We also use a logic tree, so we end up getting a curve, and that curve and that probability exceedance is just based on the weights on those logic trees. But we did different scenarios here. We did run an 8.3, and you get absolutely ridiculous numbers. But I'll show these tabulated. The other thing we plotted on this for the department is there is no data up here. There's never been anything recorded. So probabilistically, 21 feet for a 2475-year return period. I'm sorry, 21 meters, that's 68 feet, 69 feet. Wow. So again, we knew we were getting big numbers when the criteria came out like that, but my whole point is we got to use judgment in what we're doing too. We can't follow the prescription too closely without picking our head up and looking around. Deterministically, again, we're building uncertainties in all this, so we capture the uncertainty. If you look at a 50th percentile, you get 9.9 meters. Okay, not too unreasonable. We've seen that before, but it's very big. 42 meters if you look at it at an 84th percentile, more conservative number, which again is not appropriate. We ended up recommending 10 to 11 meters, and how we got there was we started looking around. What's the worldwide data set tell us about earthquake or fault displacements? So what's the largest strike slip? We're dealing with San Andreas, strike slip fault, but it's in continental crust. What's the biggest displacement worldwide? It's this Wairarapa earthquake in New Zealand in 1855. Had 18.7 meters of displacement, right lateral, or left lateral, I think it was. Anyhow, it's huge. And it's very believable based on the topographic surveys they did of these channels. And there's a stretch where there's several offset channels approaching 16 meters. Now, it's only 145 kilometers long. 1857 was, what, 360 kilometers long? 1906 was about 500 kilometers long. So this is a really abnormal earthquake. And lots of people who've done modeling on this suggest that this thing extended tens of kilometers down to the subduction zone interface there. So this is not the same animal as the San Andreas. But again, we're in search of what's the maximum that anybody's documented. We then went back and said, okay, let's look at all of the earthquakes greater than magnitude 7 worldwide in continental crust and tabulate those and update that information. So this is a China earthquake, 1931, had the average, 80 is average displacement, MD is maximum, the maximum peak on that. So on a slip distribution, you have an earthquake, you've got a maximum somewhere along that length. Doesn't mean that you're going to have a maximum at the tunnel, just there's a short portion of that rupture that has a maximum. So oftentimes average is used instead of maximum. 13.6 in this Pakistan earthquake in 2013. But again, that's the largest. So again, that gave us a basis for coming back and recommending what they should be thinking about for their designs. Again, we took those data. Purple dots are the average displacements, red triangles are the maximum, and we plotted those against some regression analyses that take worldwide data and regress magnitude to average displacement. And so these just happen to be two different Wells and Coppersmith relationships, and there's a Hecker et al. And this is from magnitude 7 and above, but all of these curves are based on a bulk of data that's down at the lower magnitude. So we're trying to evaluate what should we be confident in way up here on this end, where there's really no data. Above a 7.9, there's been no observations. So it turns out these two relationships seem to track this zone of this data set in purple, and we weighted those higher in our analysis. However, we still came back to 10 to 11 meters is something you should probably be looking at for design if you want to make this thing accommodate a future displacement. So I guess just in closing here, much of this system is over 100 years old, and it's in need of updating. The department is going after it systematically, looking at the hazard and considering mitigation options and retrofitting options for these different, or even just outright replacing. There's a dam they're replacing in Owens Valley that's about to start construction. They're probably going to replace 2 others that were constructed with old methods that are susceptible to liquefaction damage. And they've adopted this new performance-based design approach to improve the resiliency of the entire water system. I think in general it's a good approach. It just, when we're on the San Andreas and we're picking such large numbers of, say, an 8.3, I think there's a lot of folks in our profession don't think the San Andreas is capable of that type of an earthquake anyhow. But anyhow, it was an eye-opener. So I think that should be it. Thank you. Any questions? Yes.
What are the other agencies doing for the Colorado Aqueduct and the state?
I
mean, they cross 3 different places also, I think.
Yes, they do. I'm talking to DWR tomorrow. They cross the different things, open canal, parallel to the fault, so they're probably gonna be less susceptible as this narrow little tunnel.
This is the only tunnel that's crossed.
I believe so. There's also the, Colorado River Aqueduct may be in a buried pipe.
And where the Garlock falls, where it crosses the Garlock Fault, what's that?
I think it's in a buried pipe.
In there?
I don't know exactly.
That would seem to be pretty vulnerable too.
Yep.
How deep is the tunnel?
Pardon?
How deep is the tunnel?
At San Andreas Crossing, it's 300 feet below the ground surface.
How intact is what kind of inspection do they do inside of that tunnel?
So,
I mean, there have been slumpages and.
you know, they haven't had it, but it wasn't built in 1911. It wasn't the most robust, you know, steel cage and concrete. So there's concerns about even if just strong shaking, might they have some spalling and blockage, which is partly what's motivating this straw inside the tunnel design. They ran a terrestrial Lidar through the tunnel to see what kind of deformation, and the thinking was, hey, maybe we're going to see some, some flexure or bending at the San Andreas. They didn't. So didn't find much cracking. So there's no evidence of creep on the fault at this location.
So I hate to do this, but I know some students have to run to other classes, so if you need to go, please go. Scott, I think you're okay with
Y'all stick
a
around.
little chatting
Yeah.
if folks would like to do that. Thank you all for coming today. Our next speaker will be on Monday at this time in this place, and I encourage you all to come. Thank you.